So this chapter C, basically still steady state. So we are not going to deal with unsteady term yet. But what will happen today is that there will be multiple walls, right? So composite walls consisting of multiple layers. And we saw a problem with this last time. If you remember, that cylinder was convection on both ends. Well, it wasn't multi-wall, it was just one cylinder, but the two convection resistance on both sides give you basically a flavor of what happens when you have multiple resistance to the heat transfer. Multiple layer wall fluid that the heat transfer need to cross. And what happened last time? It turned out that the heat transfer was the two terminal temperature, the one to the right and one to the left, divided by all the thermal resistance that the heat goes through. The convection plus the conduction plus the convection. So it's basically as if it's really electric resistance. You know, when you have in electricity, when you have multiple resistance in series and you would like to get the current that's going through them, you basically say, well, I'm not going to solve each one by itself. I will just say those are in series. So I can replace all of them by only one resistance. That's R1 plus R2 plus R3. And the current that will go through all of them, and it will be the same current because they are in series, so they have to be the same current. The current that will go through all of them is basically the voltage across the two terminals divided by that new resistance, the equivalent resistance. Right? So this concept actually make our life very easier in heat transfer as well. If we look to a wall like this, we could don't look at K1 and K2 now. Think that K1 and K2 are basically the same resistance. So if you look at this one and that one, those are in series. The heat transfer will have to go through this one and then through the second one. And so basically it's same current, same heat transfer rate, right? So you can actually look at this guy and think, well, those are in series. Well, there is also sometimes you make the connection in parallel in electricity when they are in parallel. When they don't have the same current, but they have the same voltage across. So when they have this R1 and R2, well, they have different current that goes through them, but they have the same voltage because they are sharing the same terminal. So that's the same thing also for those two walls. When you think about it, they have to have the same temperature across because that temperature is the temperature of this material and this material. So they have the same temperature, but they don't have the same heat transfer through them. So they are in parallel. So then we could look at the problem like this and basically say, well, here is equivalent electric circuits, and we will just reduce this to one resistance and we get the current through it. And if we want the current through each one of those parallel ones, or if you would like to get the temperature in the middle, we can do it. That's the plan for today. Right? How to solve a long problem like this with electric circuits. And the second part of the chapter is basically about fins. So those fins are basically all those very long surfaces that you see at electronics and motor bike. Anytime you'd like to cool and the cooling is not efficient for you, you add all those fins. And you know why? Why would that help? Because the areas. Because we know eventually the Q by convection leaving. So the last Q is by convection. It's the air around your motorbike when you are driving on the highway, or the air that's the fan is blowing hopefully across that surface. Eventually it's by convection, and that convection is HA delta T. So if H sucks because the air is not blowing strong enough, and the delta T, you cannot allow to have the delta T to be big enough, otherwise your CPU will basically really suffer. So you have to maintain its temperature at, say, a certain, say 50, 60, whatever the degree in C. You cannot get it higher than this. So what's the only way to increase the Q? It's the area. And so that's why you basically increase all those areas. But it turned out it's not as simple as this. You are not going to get all the area working for you. Can you guess why? So say if the new area here, and definitely this new area is much bigger than the older area. Let's say it's 100 times bigger. Okay? You cannot say that the Q now will be 100 times bigger. Why? What do you think? What's the problem? Excellent. What's your name?
Cameron.
So Cameron is basically saying that the points at the tips over here, they don't have the same contact with the base like the one that's closer by. The longer you are, the higher you are from the base, probably your temperature is not going to be as hot as the one at the base. And so there, of course, because there's conduction in the process. And there is the air also around here, maybe it's having a hard time actually reaching that place. It's not like the original design where it was all exposed to air and the air can come, get hot and rise. So there are some tricks to basically what's really the right area we should use. And how we can predict the performance of the new fenned surfaces. Right? So that's the second part we're going to do today. All right? So let's go. So let's start by saying that last week we basically said that solving the conduction equation across a simple wall like this end up giving us this Q. The Q was T minus T over L Ka. Actually it was Ka T minus T over L because Q was Ka partial T partial X. And you integrate partial T partial X and it will be linear and therefore it's T1 minus T2 over the distance. Alright? So that what Fourier law will tell you if you have T1 and T2. No heat no heat generation inside, right? This is just pure conduction between T1 and T2. So I cancel K and E here and I put them in the denominator over here. Why did I do this? Because now when you look at this Q through this wall and you'd say it's T1 minus T2 over something, it's really as if you are saying the current is delta V over the resistance. Here is the delta V. It's the temperature difference in our case. Right? And did you guys get the extra? Do you have all of them here? Those last time?
No, it's
Okay. Jose is innocent. Okay. So Q is T1 minus T2 over some resistance. Let's call it R wall. So this R wall is anytime we have plane wall, so cylindrical wall or spherical wall, those will have different resistance. But plane wall, the resistance is L over Ka. Alright? So no need really to start from Fourier laws and integrate twice and or one time because there is no heat generation here. And get the constants from the bound condition. The problem is much easier than this. Right? And if there are two walls of those guys next to each other, well, it's R1 plus R2. And what's R1? L over Ka. And what's the R2 of the next wall? Another L over Ka. Right? Where L is the width of the wall. The width in the direction of the heat transfer. Right? And the area is the area normal to the heat transfer. Right? And K, of course, is the K of this material. And if we have convection, air, water, cooling on the other side by force of convection or natural convection, meaning by a fan blowing air or by just the air getting hot on its own and just rising and replacing its place with a fresh charge, that resistance was 1 over HA. H is the heat transfer coefficient over here, and we said we'll have 4 chapters in this textbook to give us this H. So let's not worry about it for now. But it's 1 over H, and area is the area, again, normal to the heat transfer. Right? How did we find about this? Well, that was the last problem we solved last time. At the end, the heat transfer resistance was 1 over HA. If you remember, the cylinder has 2 pi RL. That was the area. It's the circumference times the length. That was the area of the heat transfer. And it turned out that the resistance of convection was 1 over HE, that area. All right? So that's always the case. Right? So anytime you see a convection, it's 1 over HE. And this will apply to plane wall, cylindrical wall, spherical wall. The only difference is the area would be different, right? So for cylindrical wall, it's 2 by RL. For spherical, remember 4 by R square? That was the area of the sphere. So just the area would be different, but it's the resistance of convection to heat transfer is 1 over HA. Okay, so that's typical situation where you have convection from outside, natural convection say outside, conduction here, and another convection on the inside. So now to get that Q through the whole thing, you do it like what we did last time, and you integrate, and remember the boundary condition on the convection was not really easy to solve, because you have, remember how did we do them? When we are integrating the equation, the conduction equation, over here we need the boundary condition at this place and boundary condition at that place. We don't need, actually know T1 and T2 when we solve a problem like this. So how can we get the boundary condition? We used to say anyone? Does anyone remember? If T1 and T2 were given, it will be just T equal T1 at x equal 0 and T equal T2 at x equal L. If it was convection, we used to say
Q convection equals Q conduction.
excellent. Q convection, which was H multiplied by the area time this T minus this T that we don't really know, equal to Q by conduction here, which is minus K partial T partial X at this place. So the boundary condition was really annoying, because it was a boundary condition for the gradient, not for the T. It's not as simple as T1 is 5. Here you go. Get your C1 and C2. No, it was K partial T partial X equal H T infinity minus your T. Now solve for your T. Right? And you do it twice, and the problem was really, really horrible. It was a little bit long, right? Well, maybe not really horrible, but it was long. So now we look at this problem and say, wait a minute, those are 3 resistance in series or in parallel? Series, because the Q that goes through this, exactly the Q that goes through this, exactly the Q that goes through this. There is no storage. So if there is 10 watt going here, there will be the same 10 watt going there, there will be the same 10 watt going there. Right? So 1, 2, 3 resistance in series. What is this guy? 1 over HA. What is this guy? 1 over HA. Its own H. Huh? And what is this resistance? L over KA. You don't really have to memorize, since the exam is open textbook. But it speeds you up if you actually know that it's L over KA and 1 over HA. Right? So, you had a question.
In these examples, the area on each side is the same, but if you have a cylinder with like concentric materials, what area do you end up using?
What's your name?
Jason.
Jason, question is, this area here and this area here, the area that you're using 1 over HA and 1 over HA, H1A and H2A, those are the same area, because it's a plain wall. You can imagine if that wall was 5 by 8 meter, the other wall would be 5 by 8 meter. It's the same area. As a matter of fact, you can just cancel the area from everywhere and get the Q per unit area. And then eventually just multiply by the area. Because the area here is the same, the area here, the same, the area here. But then Jason's question is, well, what happens if it was a cylinder? Or spherical shells. So one spherical tank with multiple layer, foam and then, I don't know, steel and then foam and then tile or something. So those will have different area, right? The inner area is smaller than the bigger area. Well, the answer, so the question was which area you should use. Well, the answer is use the area that is heat transfer is happening on. So for example, if in this side, H1 should be multiplied by area 1. That will be the area here on the surface. On this side, it will be area 2. The outer, or if this was the inner side, use this area. Now, Jason's question immediately should be now, but what happened in the middle? Well, the middle, it's not going to be like this. This is only the resistance for a plane wall. The resistance of conduction in a spherical or cylindrical shell will have actually R1 and R2. So it will not have area. So your problem will be solved for you. So let's wait until we go there. Other questions? Right. So now one can actually look at those three guys together as one just big giant resistance, right? And this one big giant resistance, actually we can call it 1 over UA. Imagine this R, take this R here and make it 1 over UA. So the R total is 1 over UA. What is U? That's the overall heat transfer coefficient, right? So that number is really useful for, say, someone designing a heat exchanger where the water from the hot side is heating the copper wall and then going to the cold side, for example. They don't really want to worry about all those layers and integrate the equation and they just want to find out what is the number that represents the resistance to the heat transfer. And that number is U. Okay? So it's simply, the Q then would be delta T over 1 over UA. All right? You don't have this slide, right? That's okay. So let's solve one problem and then we'll go back to this. So let's solve this problem. I give you this problem before we start. So in this problem, there are three resistance also. Let's read. So this is basically the glass of your car, right? And so you are sitting here in your car, all right? And there is ice outside across and then the windshield, the glass windshield. So this is glass. And the glass has a K of 1.4 watt per meter square, all right? And the air outside is minus 10. So this minus 10 is T infinity, right? It's the convection side. So let's call it T out infinity as compared to Ti infinity. So that's the inner temperature and the outer temperature. And there is, of course, convection over here. And then there is conduction of the glass, and then there is convection again here. So convection on the outside, conduction through the glass, and convection on the inside. All right? So the air inside is at 25 degrees. Your cabin is hot. The heater is doing a good job. The air outside is minus 10 degrees. So 25 degrees here, minus 10 degrees over there. All right? And the Q would go which way, do you think? The Q will go from the 25 to the outside, right? The heat transfer will flow from the hot to the cold. All right? And so what do you think the temperature on the inner side of the glass? Can anyone give me a guess what would be that temperature? The temperature on the inside of the glass? Just give me a number that makes sense. Right? So Mallory is saying that it should be less than 25. Why did she say 20? Because she thinks there's a resistance between the hot air and the glass. That resistance is, can anyone tell me what is that resistance? 1 over H. I don't want someone to say 1 over HA. Which H? The inner H, right? This H, the fan that's forced convection, whatever the design that's blowing air on the glass, and whether they are doing a good job or not blowing on the glass, right? So if doing a good job, they should have like vents really directed on the glass to make sure that all the air goes there. All right. And what do you think the temperature is on the outside surface of the glass? Give me a number that makes sense too.
2 degrees Celsius.
That would be, so Jose saying 2 again because he didn't go all the way to -10 because he realized there is a resistance in between them, 1 over HA, which H outside, whatever that H outside is. So he realized that it cannot be the -10. It has to be a little bit higher toward the other guys.
Or else it'd be ice on the glass.
That's another thing actually. But so forget about the ice now. So for sure the temperature on the outside surface cannot be the air, the outside air, right? Because there is a resistance between the two of them. Now what we as a designer would like to have, 2 would be perfect. Actually 0 is good enough for us. Why 0 is good enough for us? Because the whole idea was that you would like to melt the glass on the outside. Or basically you'd like to make it harder for the glass the ice to form on the outside glass. Any ice that should drop basically should melt, right? So that's what he's asking exactly for, right? So warm air is blowing over the inner surface of an automobile windshield is used for defrosting ice accumulated on the outer surface. Convection heat transfer coefficient for warm air blowing over the inner surface is to be determined. So he would like to figure out how much is the heat transfer on the inside to make this happen, or basically to raise the temperature on the outside side of the glass to be 0 or higher, right? So if he can figure that H, again through the equation that we will learn later during the course, he can track back what should be the velocity of the fan that will give him that H, that will melt the ice. And so he can design the vents on the windshield that's necessary to actually make this happen, right? So that you can melt the glass without really boiling yourself in the cabin in the winter. All right. So before actually, what did I do? So before we solve this for this H, let's just draw a cleaner picture of this. Right? Those are the 3 resistance that I have. And this is that 25 degrees C, and this one is -10 degrees C. And it doesn't really matter whether it's degree C or degree Kelvin. Remember Jesse asked about this last time? Because eventually we are going to say Q is delta T over the R's. So delta T in Kelvin or delta T in degrees centigrade will produce exactly the same number. All right. And this 1 over HI area, this is actually not really known. Okay? The R resistance is L over KA, and that's given to us. L is given and K is given. The K is 1.4 and the L is 5 millimeter glass. Right. And 1 over H out area is given. And notice there is no area out and area in. It's just the same area because it's plane, or at least approximated to a plane wall. All right. So can anyone help me solve this problem? Is there anything else that's given to us? Anything else that I can put in that sketch? One more piece of information is given to us.
Oh, we need the temperature of that document.
Right. This should be 0 or higher. All right. So now, any problem like this, multi-layer of conduction, there is only one equation that solves these problems. All right. And that equation is, of course, Q equal delta T over all those resistance. Right? We are not going to start from Freire law and integrate anymore. Right? Those problems are easy enough for us. We know the solution. We will do this in your homework that's due on Wednesday because we don't know the solution, because the wall is actually having this weird heat generation rate that doesn't make the solution the standard solution. But those walls are standard. It's just conduction over a plane wall. So the Q is delta T over its R, and that's it, right? So here is my Q. So I'm going to make it per unit area, I guess. Doesn't really matter, but well, let's make the whole thing. So Q dot is the 25 minus 10 ouch, my line, over 1 over H out area plus L over K area plus 1 over HI area. And this guy I don't really know, but I don't even know the Q. So in this equation, again, all the problem of conduction, multi-layer conduction, will be solved like this. He could basically give you most of them and ask for only one of them. So he can give you the temperature and the resistance and ask for the Q, how much heat transfer is going through. All right? Or he can give you the Q and the delta T and say, well, how thick is the insulation that will do this? So he can then ask you about the L. So there is no really surprises here. There is this one equation. You need to have everything known except for only one variable, and that is what you are trying to calculate. So it's not okay to actually have two unknown. That doesn't help. So can anyone solve the problem for me? Can anyone give me the Q? So I can get my HI. Excellent. So Mallory is saying you can actually get the Q. Say you want to do the conduction, so because you realize this Q is the same. Actually, let's do it in the right direction. So that Q is the same as that Q is the same as that Q. Why?
Because they're in series.
Because they are in series. They are not storing anything in the middle. So if you get the Q from any one of them, so now we are doing it for the whole thing. We cannot do it for the whole thing. Why? Because one of the resistance is not given to us. So see this one. This one we don't know it. So we cannot do the Q for the whole thing, but we can do it for maybe this guy by itself or this guy by itself, or so which one you suggest we should use or get? The one from this to this, because this is the one with, why do you like this one?
Everything's known.
Right, you know the two resistance and you know the temperature. You know the two temperature and you know the resistance. So basically it's the same Q, right? And therefore it is the 0 minus the minus 10 over 1 over H out area. All right? And of course H out is given. Now you could wonder, well, what is the area? Well, it doesn't matter. We don't really need the area. Let's cancel the area from all of them. Let's get it per unit area. So you get the Q per unit area, or basically a small Q dot from this side, and you can basically get the H from here. Does this make sense? All right, what is the final answer? So HI is, let's make it in red. So HI is 1112 watt per meter square Kelvin. Okay? Okay, very good. Just making sure I'm recording. Very good. So this is actually, this problem was a little bit tricky. When you don't really know the temperature in the middle, then you have to get the Q from only part of the wall. But usually the problem is much easier than this. Usually the problem is you know the two temperature across the two ends and you know the resistance in the middle, get the Q. right? Or you know the two temperature on both sides, and basically there's just one resistance that you would like to calculate so that the Q is a certain number. Okay, like for example, your homework. So let's look at your homework quickly. So that's yes, homework 2, no, which was in the exam last year. So look at this. It's a wall of a furnace. He give you the area of the wall. 2 meter by 1.5 meter. And the temperature on the outer surface is to be maintained at 110. The temperature of the room where the furnace is located is 32. Convection heat transfer is 10, so the resistance of the convection is 1 over HA. You have the resistance of the convection. Radiation heat transfer is neglected, okay, so only convection that take care of the heat transfer. Is proposed to insulate this section of the furnace wall with glass wool insulation, and he give you the key in order to reduce the heat loss from the outer surface by 90%. What is the needed thickness of the insulation assuming the furnace wall is 110? So basically he's saying there was this wall, and the wall is sitting at 110 on one side, and there is air convection by outside, and he doesn't like the heat loss from that wall, because that heat loss he need to compensate. He need to keep the furnace hot, so you will have to burn more fuel, as if you are doing a grilling, you know. And if you buy a very cheap grill and the grill cover is hot as hell, guess what? You are basically paying for that heating of the cover. But if you buy a very heavy, you know, expensive grill with a very thick wall, it's very hard for the heat transfer to go actually across that. So you don't have to pay as much to maintain your temperature inside that hot. That's the scenario over here. So how we can reduce that heat transfer? He would like to reduce it by 90%. So the new Q is 10% of the old one. So first you solve the old one and you figure out, well, it's 100 watt. Okay, he doesn't actually want 100 watt. He's not happy. He only would like to have 10 watts keeping. So how much is the new wall? All right? And it's conduction plus convection next to each other. So Q is delta T divided by the two resistance, adding them to each other. Does this make sense? Okay. No, this is not the right one. Okay. So back to the. All right. What if we actually like to calculate the temperature in the middle? Like for example, let's go back to this problem. What after we are done, he basically said, and we calculated the H and everything, he said, so now the outside surface of the glass is going to be at 0. We did this. What is the inside glass temperature? So what is the temperature over here? How can we calculate that?
Well, if we have the Q's all the same, we just plug in the numbers for LKA, and then 0 will be our T.
Correct. So Brandon is saying, well, if you want that temperature, you already solved for the Q. That Q that you solved for from this side or from the whole thing, that Q is also the same over here. So we can get this temperature by saying that Q dot per unit area, or not by unit area, just the Q is, it's that T inner minus the 0 divided by L over Ka. The two temperature, this guy minus this guy divided by the resistance between them. Correct? We can also do it from this side, because again that Q that we solved for, it's also 25 minus this guy divided by what? 1 over HIA. And we can also get that guy from doing those two guys together, right? We can say the same Q here is this temperature minus the minus 10 divided by this plus this. So you can slice it any way you want, right? So those two are in series, those two are in series, and the three of them are in series. And it's the same Q going through each one of them and through all of them together, and any combination of the two of them. All right? So that's what you do if you would like to actually get, say, the temperature in the middle. So if the problem is given like this, and in this scenario, T infinity 1 and T infinity 2 is given, and you would like to calculate the temperature in the middle, and you have all the wall geometries, meaning the K and the L, and the H and the A and everything. Well, first you start by saying my Q through the whole thing is, let's start from here all the way to here, divided by 1 plus 2 plus 3 plus 4. 4 resistance. Convection on this side, conduction through this wall, conduction through this wall, and then convection on the other side. So doing this will give you the Q. So that Q is also the Q through only this guy, meaning T1 minus T2 over that resistance, and that gives you this temperature. Okay? Question about this? All right, so the whole secret is just to realize that, to keep in mind that this Q is the same as this Q, is the same as this Q, is the same as this Q. It's the same Q. All right. Now, talking about interfaces, if there is actually perfect interface, you know, if you have perfect interface, then T1 is equal to T2. But if there is air between them, T1 and it's not going to be equal to T2 too, right? Because there is actually air between them. So having an air like this, an air layer, or maybe a film of another liquid, for whatever the application is, if this interface is filled with the other fluid, that reduces the heat transfer, or basically add an extra resistance to the conduction. Right? Sometimes you do it on purpose so that you want to do a good job insulating your house, you basically put all those layer of insulation, right? So that you wouldn't have that much heat transfer. And so the air is really very, if you trap some air between them, that's a good job actually, from the heat transfer point of view. Air is not really conducting that good, right? Or that well. So the resistance of this air layer is basically called the thermal conductance. So they give it in the form of 1 over HA. All right? And so from our calculation point of view, we'd basically put this in units of resistance. So by the way, what is the units of the resistance? Can anyone tell me? So those resistance that we have been talking about, 1 over HA and L over KA, what do you think the units are? Just look here and tell me. Look at this and tell me what should be the units.
Kelvin over watts.
Say that again.
Kelvin over watts.
So it would be Kelvin over watt per unit area, right? Because that Q is watt per. Sorry, no, you are right. It's actually Kelvin over watt, correct? Right. So here is the units for the H, right? For different material. So if in case there is an exam problem that will has to deal with this, I will basically tell you what is the material, and then you can look at that table and get the H. And so this will just be one area that you put it in the middle, or one more resistance that you will insert in the middle. Okay? All right. Let's solve another problem. So this is a coat, all right? And so the coat is made from layers of material and air, material and air, material and air, right? Because you think air is doing a good job insulating the or reducing the heat transfer. And so eventually there is the air outside at 0, and there's convection between you and the air, or between the coat, outer surface, and the air, and here is you. So you are sitting at 25 degrees. All right? And so those are 5 layers. So 1, 2, 3, 4, and 5. So 5 layers of 0.15 cotton fabric. So 5 layers of cotton fabric, and they trap between them 4 layers of air, and the air is 1.5 millimeter. So 0.15 and 1.5, 0.15 and 1.5 air. All right? And the result is basically, so he would like to calculate the rate of heat loss through the jacket is to be determined. So how much is the Q that we'll be losing to the outside air? And if we are going to replace the whole thing with a single layer of wool, so the wool, look at the K here is 0.26 of the cotton, and the K of the wool fabric is 0.35. No, yes, 0.35 for wool fabric. So if he, rather than having this design, if you are going to have just wool fabric, how thick it should be so that it could have the same heat transfer. Alright, so let's solve the first one first. The first one is the Q of this jacket with this design. So the electric resistance equivalent to this is already drawn for us. It's basically all those resistance, right? Cotton, air, cotton, air, cotton, air, cotton, air, cotton, and then convection on the outside. So this last one, what is the resistance here on the outside? This resistance is, how much is it? No, I want the expression to get it. It's like, for example, those guys are L over Ka, right?
Yeah, 1 over
HA, correct? So the rest is basically, you can just write L over Ka, 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 L over Ka. Or if you are a little bit smarter, you would say, well, it's just 5 L over Ka cotton plus Y plus, because they are in series, plus 4 L over K air plus convection. That is the resistance we are dealing with, right? They are all in series. They are basically, we can replace them by 4 air plus 5 cotton plus 1 convection. Correct?
Take all the A's out of it.
Right, you can take all the A out of them. That's very true.
Why aren't you giving A?
So let me see if we're actually given the area.
Because it says right above the.
Yeah, we are given the area. It's 1.25 meters square. It's not given here for you, but it's given in the textbook. So this problem number 64 in the textbook. Right, the area is right. It's written there, 1.25 meters square. Correct. So we can just basically say R cotton is 5 L over Ka, of course cotton, so that's 5 multiplied by the L is 0, 0, remember using SI units, 1.5 over 0.06, 1.25, and R air That's basically 4 times L. When I say L over K, I mean L over Ka of the air. So that is 4 multiplied by 1.5 times 0.026, 1.25. And eventually our convection is 1 over HA, so it's 1 over the 25 times 1.25, and Q dot jacket would be the T1 minus the T infinity over our total, or basically let's add all those guys together, and so that Q will become 110 watts. So you lose 110 watt. Every second 110 joule will leave this jacket with 1.25 meters square. So now if we are going to replace this by just one big or one thick layer of wool, the H convection is still the same, 1 over H out area. So this guy LKA wool sorry for my handwriting, but it's the first time I actually use this guy. I have a much bigger one actually, but doesn't have wireless. Anyway, so it's this L that we are after. He's going to replace those 5 layers. So T1 is still the same, right? T1 is still the 25 degree. And the T infinity is still the same. That is the, how much was it? 0. So the question is, how can I get this L, the thickness of the new layer? So equivalent wool jacket thickness. Can anyone help? So that Q that we just calculated, Q wool, should also be 110. He's saying, well, how much is the thickness to get 110? Okay, this should be equal to what? What is the Q now in this scenario? Anyone? Right, there are 2 temperatures and there are resistance between them. The Q that will go through this new design is the temperature difference divided by the total resistance, right? 2 layers or 2 resistance in series. What are their total resistance? Let's add them together, correct? So it's simply the 25 minus the 0 divided by L over Ka wool plus 1 over H out area. So what do we know? We know the H out we know the H out, and we know the area, and we know the K and the A. The only thing is the L, and the L is 8.52 millimeters. Look at that. So rather than, what did we used to have? We actually had 0.15 millimeter thickness of this fabric, but actually 5 of them. Okay, but so 5 times 0.15, that's not even 1 millimeter, right? And you have to replace it with 8 millimeter of wool. Why is that? Because the air. Because actually you depend on the air to kill your heat transfer. All right? Can anyone solve this problem a little bit shorter? Again, the same question here. If all we wanted is how much is the thickness of the wool fabric that would do the same heat transfer? Is there any way we can get this a little bit shorter? So you have only 2 minutes in the exam and
The resistances equal to each other. with the
excellent. Excellent. So Mallory is saying that you are replacing the layers of air and cotton with this wool. Forget about the convection. It's the same everywhere, right? Forget about this 0 and 25. It will not really change. If you can just think about this new resistance over here, if I can. If you just think about this resistance over here and what it's going to replace. So this new guy with wool is supposed to be replacing 5 of those guys, right? Maybe I don't really need to plot 5 of them, but so there are 5 of this. All right, so all you have to do is basically just say, since we are running out of air of time, you would say, so our wool is going to be 4R air plus 5R cotton. And those you calculated from the last problem. Remember we had to calculate them here? 4R air, and so you had those numbers already. So you just basically set this equal to R wool, and that R wool of course is L over KA wool. So this is a 1.25 meter square, and this K is the 0.035 watt per meter Kelvin. So really the only thing that's unknown is this L. You get that L. Alright, replacing those 9 resistance with just 1 resistance out of wool. Question so far? Alright. Now the parallel, we know again in from electricity that it's not the same current that will go through the two of them. This will be 2 different heat transfer that will go through them. So Q1 and Q2 will not be the same, but T2 and T1 would be the same. Why T2 and T1 would be the same? Well, because the material over here, the neighboring material, will force that on them. Alright? What if the scenario where the T in this edge is not the same at that edge? Well, then they are not really in parallel. If they are the same temperature, they are in parallel. If basically it's another temperature, so maybe this would be in series with this guy, and the 2 of them are in parallel with the other 2. But in this scenario, when this temperature is the same, and this temperature across the whole edge here is the same, then they are in parallel, having the same temperature across. All right. So in electricity, we used to replace this with the equivalent resistance, which 1 over R total was 1 over R1 plus 1 over R2. So you can do it like this, or basically you know that this is equivalent to this, R1, R2 over R1 plus R2. You remember that from electricity? All right. So this is how we can get the R total of those 2 guys together. And from that point, it's the same thing. If you want to get the Q through the whole thing, all right, you basically do T minus T over the total resistance. If you would like the Q in each one of them, or the resistance of each one of them, you solve each one of them by themselves. All right. So sometime it can be 2 in parallel with the next guy in series. No problem. You just basically reduce those guys to their R equivalent, and then it's series with the rest of the group. Right? Like for example, look at here. They have conduction in this and this one, and then conduction here, and then convection. So they reduce those two guys together into one resistance, and then conduction with this 3, and then convection on the outside.